So, remind you where we were. So we're looking at parallel axes and radial axes, largely for identifying groups, but also for, in the case particularly of parallel axes or parallel coordinates, you can actually see some geometric structure, and including correlations, since correlations are points near lines. So I also encourage you to go through this one yourself. Play with that, the parallel coordinate point line. So that's great for high dimensions, and for high dimensions, if it gets very high, much higher, if we have measurements, we can think about doing Eulerians, we can think about Hamiltonians, etc., just as we did before. Now, the thing is, what if the, I probably should just make that point. That, of course, if you like, because the glyphs are here, I could change these to parallel. So we have the little mountains like we had with Dan Carr's data here. So we can see that the mountain ranges representing the different dimensions with the axes. And again, just to be comparable, where is it? Parallel. Right? So you can see it there. So either axis system can be placed on top of the Cartesian and made interactive. So what if the dimensionality gets much larger? So maybe it's thousands of dimensions. Can we have a glyph that kind of captures many, many dimensions? So one possibility is to think about a rectangular array. So I in fact have one point in high dimensional space, and I map that point to just a single array, where every coordinate of the point gets mapped into one cell in the array. Okay? So think about it. Every coordinate in my vector, my point vector, is given a position or a pixel in an array, a square in an array. And I use what's sometimes called a heat map, and the idea here is that now the coordinate the position in the vector gets mapped into a position in the array, and the value that's in that coordinate, the numerical value of the variate, gets turned into a numerical value of the variate in the array, but presented as a color. So I'll map it into a color. Okay? So every tiny square is going to be encoding the value through a color. And what I need now is a way of mapping the coordinates to the array. So you could just populate it by row if you like, but that kind of destroys some things. So what I'd like to have is, if at all possible, some desirable things. I'd like, if it was a coordinate near it in the vector, I'd like it also to be near it in the array. Two coordinates that are near each other in the vector, beside each other, I'd like them maybe to be beside each other in the array if I can help it. So I'd like to preserve the order. I'd like to go, because imagine that this vector, for example, was a time series, right, where I want to preserve time. I'd like to go down this way and be able to find a nice path in the array where nearby time points were also nearby each other spatially in the array. But I'm going from a one-dimensional array, the vector, to a two-dimensional array. So I'm going to break something. It's not going to work, right? So at some point when I have to change rows, something's going to go wrong. So say, how close can we get to that? And so there's some things that we can grab from math, right? How many people have heard of space filling curves? Anyone here of space? Okay, so you can imagine, for example, the plane So a curve, think of a parametric curve where it's any curve in the plane. It's not a function or anything. It's any curve in the plane that is parameterized by just how far along the curve are you. The idea is, can you get a curve covers the whole plane? Every point on the plane is covered, but it's still a curve. You can tell how far along you are. If you can do that, it's a curve that's filled the space. It's a so-called space-filling curve. And there are a couple of these that are well known. Certainly Hilbert piano curve is a very famous one that is easy to describe. Another one is a Morton curve, and one that's more recently proposed, just some recursive rectangles by a fellow named Kine, that will be useful to use. So let's have a look. So we're not going to have a whole, don't look at this too much right now, but we're not going to have the whole plane, this whole infinite dimensional sheet. We're just going to have pieces in an array, right? So we're just going to have a finite number of fixed positions on a rectangular grid. So say I had a 4-dimensional data point now. That means I can have it map onto a 2x2 square with that 1, 2, 3, 4. Okay? That's following this curve. 1, 2, 3, 4. So if I only got 4 things, I'm done. 4 dimensions. If I have many more here, I've got 16, right? So I've got a vector of 16 elements. I'm matching this, so we're following the rainbow colors if we're looking at where are you on the parametric curve. And I've numbered them here. So it's going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So we're following this curve. And you can see how this curve's built. This curve's built up by a whole bunch of these little U's, effectively, right? And then joining them together. So U here, a U there, a U there, U there, and then joining them. And that becomes recursive. So the next step, and you'll notice that this is level 1, level 2, level 3, because it's always going to be trying to fill a square. So this Hilbert curve is going, we're just following in here, and every corner or every space here, every point on the grid is going to be a pixel. So this is going 1, 2, 3, 4, 5, 6, 7, 8. Doing this right? Nope. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, etc. Just following this thing. All right? So that's a parametric curve. So now my vector of, what have we got? I could have a 64-dimensional vector here. And its first element will be placed there, right? So if it were a time series, I'm going to see time 1, time 2, time 3, time 4, time 5, time 6, time 7, time 8. So roughly speaking, if they are near each other, very close to each other, 1 or 2 time units apart, they're going to appear near each other in this plane, okay? But if they're near each other in this plane, it doesn't mean that they're necessarily near each other in time, because this point is near that point. So that's what I mean, something's broken. But it's close. Everybody get that? So now I can take one 64-dimensional on the right point in 64-dimensional space, one coordinate vector, and map it into a square. Okay? Everybody with me? So that's one way of doing it. Yes? So the first 8, in the first row, then number 9 is here. Number 9 is really far away from 8. Whereas if I did this, then 9 is close to 8. If I went like that, even, it would be closer, right? And this is some way of trying to get this in a nice recursive fashion. So you can see there's a doubling, there's a quadrupling actually, but a doubling of the side here every time. And I can imagine taking this, all the values here, and replacing it easily by the average of values nearby and getting this on the left. So there's some preservation of order. Not perfect. Yeah. Correct. So it's going to sit there and it's going to travel along until it runs out. Okay, so if there are fewer, so here we have 16. If there are only 9, it's going to go along doing this, 5, 6, 7, 8, and it'll end there. So it'll be a little ragged. Okay. All right, here's another way. This is the Morton curve. So now it's going to be 1, 2, 3, 4, the Z. Up here for 16, I've got 1, 2, 3, 4, 5, 6, 7. And now we're going to have the problem that was just suggested when we did the rows. I'm going to go 8, zipping all the way over there. 9, right? So following this zigzag, and then have to go back to the other side. So those are really far apart spatially to each other. Yes. So if you imagine this is my vector y. How many have I got? 1, 2, 3, 4, 5, 6, 7, 8, 9 to make the example. I want to turn that into a square. So this guy goes there. This guy goes to the next one, which is right beside it, right? And the position is going to follow that curve. And what we haven't done yet, because I've just used the rainbow to, again, let you see what the order is of the squares. These will have values, and I'll replace these values by colors. So now I'll see, I know I've got a standard layout, and I'll see the values by the colors. Produce a heat map. So this is another one that has clearly got some abrupt changes. One more. This is Keim's proposal, fairly recent proposal in the 2000s for visualization purposes. And Keim's view is that we often have ways that we would like to specify the layout. So here we're going 1, 2, 3, 4, 5, 6, 7, right, just like that. 1, 2, 3, 4, 5, 6, 7, 8, 9. And the specification is I want something that's going to be a width of 3, that's 3 columns, and a height of 3, that's 3 rows. The next specification is it's a width of 3, 2, and a height of 3, 2. And that's telling me how I want to change these things. First, it's going to be a 3 by 3. And then that group I want to be organized as 2 by 2. So 1, 2, 3, 4, 5, 6, 7, 8, 9. That's my 3 by 3. Now think of that as a block. I want to repeat that pattern, but have it 2 wide and 2 high. So 2 by 2. So go 1, 2, 3, 4, 5, 6, 7, 8, 9. Back up. 0, 1, 2, 3, 4, 5, 6, 7, 8. Over here, 9, 10, 11, 12, etc. Just following this path. So this parameter here is allowing us a little more control over that layout. And it need not be square anymore. So here 322, 322. You can have really complicated, and you really want to follow the rainbow colors to get a sense of where the order is. So going through these reds here first, up to these oranges, right? Over these orange yellows, yellow greens. You can see how it's moving around. Just following this curve. Okay? So far, so good. So that one's got a little more control. Yes? So ideally, you'd like to have the order, at least imagine an order following here that preserves the order of the coordinates. One. You'd like to have, if you're near that coordinate, if the coordinates were near in space, that they'd all be near each other spatially. And all coordinates, all the time. You've got some natural, particularly this one, natural mathematical layout for things that is nice and recursive. They're all nice and recursive. And this one gives you a little more control. And so I'm avoiding your word optimal because that would require an objective function of what I'm trying to optimize. You see, in a second, we'll just look at a couple of examples and it'll make a little more sense. Okay? That this is actually, particularly for time series data, this is actually a very handy layout. Okay? So let's look at an example. So this is S&P 500 data. And S&P Standard & Poor's, it's a index looking at stocks and their prices. And so we're looking at the price of 500 roughly different stocks over some number of years, their daily closing price. So we have their daily closing price 5 days a week over several years. And we have lots of them. So every stock is a point. So the dimensionality is, I think, I use here. So I use 3 years, 2007 to 2009, 3 years of data. So however many days there are in that time period, by that I mean weekdays, operating days, that's the dimensionality. Okay, so roughly speaking, think of 5 times 52 times 3. Roughly speaking, that's so every point is in that big a dimensional space, and each point is a different company. Okay, and their position is determined by what the closing price was on each day of those several years. Okay, does that make sense? So this data has 756 dimensions. And we've got several stocks. Not quite 500, but close. Because if we look at ones that just are complete on the time period. All right, everybody get it? Each stock is a point in very large hundreds of dimensions. So, for example, this looks like each column here is a stock. That's the ticker abbreviation. And this is the closing price. So these are the first 7 days. Some of them have got missing data, so we're not going to look at those. We're going to throw those out. And that's what I'm doing here, getting the complete cases and omitting things that have NAs. Just to get this down. So the first 3 stocks that I have here that don't have missing data are these ones 61.9, 61.7, that's this MMM stock. Next one is 18.4, etc. That's the ABT. And you can go look these up on Wikipedia or S&P. So ABT is short for Abbott Laboratories, for example. Each one corresponds to a company. Okay. The other thing that's available in this data set are sectors. So we in fact know, I should have mentioned this data comes from what our package, QRM data. So you can access this, and each one has also a sector and a subsector. So Abbott Laboratories, it's in the healthcare sector, and the subsector is healthcare equipment and services. So we know groupings. So we'd like to see, you know, what do these guys look like if they're in the same sector? So in some sense, there should be, we got these points, roughly a few hundred points in 700 and some odd dimensional space, and we know they're in different sectors. You kind of expect them to behave alike. That is, they'd be near each other in that high dimensional space. Okay? So here we go. So I've got some, I'm looking at particular sectors that I'm going to look at are banking sector, pharmaceuticals, and oil. So oil and gas exploration and production. So I'm going to need to get the number of banks that I have, the average over for each sector. I'm going to get the average of the stocks in that sector. So that'll be another point in high dimensional space. So I'll do that for the banks, for the pharmaceutical companies, and for those involved in the oil sector. And I'm going to produce a data set now that has just those sectors and the average in each. Okay, everybody with me? Yeah? So now I'm going to start having glyphs, and I'm going to have to figure out how am I going to map the values to some colors. And I'm going to use a divergence scale from red to blue. Blue is above the average, red will be below the average. Okay? And use our so we use make draw glyphs. We can make any glyph at all in the glyphs package that's on the website. You can also use this make glyphs. And I'm going to take those data subsectors. Say I want to have a Hilbert curve. I want these to follow a Hilbert curve, or I want them to follow a Morton curve. Very easy. Okay? And that'll produce some layout. And that'll be based on, because it's after a square, it'll be based on the trying to fill out as much of that square as possible. With the Kime, the recursive rectangles there, those height and width parameters can be used in a natural way for this data. So in particular, this data set, I can use this width vector and this height vector. And what does that mean? Well, I want you to look at the columns, 5 by 1, 1 by 4, 12 by 1, 1 by 3. So the first bit, I'm going to organize 5 columns of one row. That's a week. Once I've got a week, I want to organize those into one column of 4 rows. That's a month, more or less. Once I've got those, I want to take that month and put them in 12 columns in one row. And then I'm going to have 3 rows for 3 years that we're looking at. So this Kime thing allows me to dial this up and get this so it kind of makes sense, and to lay out like that. So what we have here, if you look at it, it's going 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Back up, 1, 2, 3, 4, 5, just following the rainbow colors. And they're all lined up, so in fact, every column here is a Monday, or at least the first of the 5 days. The next column, all Tuesday, Thursday. So the first day of the week, the second day, the third day, the fourth day, the fifth week. If I take 5 columns together, that's roughly speaking the same month, right? So I've got days lining up. The first day of the week, second day of the week, third day of the week. I've got all of the months lining up. And horizontally, first year, second year, third year. So now it's got structure that makes sense for this data set. That's the beauty of the Kime. Let's see if we get through this. So that's simply the Kime with these height and widths. And I've write this function that's going to lay these all out, that's imaginatively called doit. And we call doit on any of these glyphs that we've just made. So on the Hilbert space, and I can do it on the average. I can get the average of the indices if I just need to find out where are the averages, where are the banks, where are the farm, et cetera, so you can follow things. So here we have, this is looking at the averages in the Hilbert layout. These are the averages for banks, for pharma, for oil. And so it's a question of how do they look different from one another? You know, they clearly look kind of different. I remind you that this data overlaps with 2007, 2008, 2009, overlaps the last big crash, right? I think it was what, October of 2008. So that's when we had the last big financial crisis. So there's a Hilbert layout, and it doesn't get the full square. Similarly, whoops. What a stupid thing, Java. The Morton layout, also seeing this, and so you can see that, you know, this big red block when it's below average, you know, banks have got this huge chunk that's below average. The pharma, not so much. Oil, not so much. Where this gets interesting is with the Kime plots, because now we can see 2007 going across 2008. Things start coming off here with this red. Banks hit really badly, right, with stock prices here. Pharma not doing nearly as well. Look at how well the banks are doing up here, right, at the beginning of 2007. Pharma not so, you know, they're okay, average. They get a hit here, but they don't get hit quite as badly as the banks, and the oil's not nearly as bad as either, but they're not doing outrageously good like the banks were doing up here, right? So you can actually see a difference between these sectors just from that, and those are 3 points, the three averages in 52 dimensional space. So let's just go see if we can just get through this. So looking at, these are all of the banks. These are the different banks involved, so you can see how some banks fared compared to others. They do all look kind of like with sort of a blue stripe, a white stripe, and a red stripe. But some banks are clearly were doing better earlier on and did worse later. And some were not that affected, nearly as affected. JP Morgan, for example, here. So two things. You get to see, do they look a lot alike? Do they have similar kind of patterns? And can you, knowing that this corresponds to time period, so this is all of January, this group up and down here, all of December at the right-hand side, see what's going on individually. And these are the pharmas. Again, some pharmas, this looks like Eli Lilly, I think, hit worse than other, but slightly different than the banks. And those are the oil companies, and that looks quite different patterns from the banks. So you're seeing where these guys are in high dimensional space. So that's an example of a heat map using space filling curves to be able to map this in so that you can at least see glyphs, and sometimes some structure, like when you've got something like a time series where you can lay it out in a meaningful way, you're in business.